now I'm going to teach you a very powerful trick called as the reduced mass trick to solve a certain model of problems. This is not a very common trick, by the way. Let's see what this trick is. So you have this capital mass m, you have the small mass m, let's say this height is h, right? This height is h, right? Now if I give it a certain velocity so that it goes up like this and just stops here, it doesn't go further, right? And what will happen at the same time is they both will move with some common velocity. Now the question that I want to ask you is, what should this velocity be so that they start moving with a common velocity? And we can also ask, what should the common velocity be? So how will you solve this particular problem? There are two things that you will do. First, you will apply conservation of momentum, right? Conservation of momentum. Why will you apply conservation of momentum? Because there is no external force acting on this, so there is no external force acting in the x direction. So x direction velocity momentum must remain conserved. So your first equation will be something like this: mv towards this side, towards minus I cap, should be equal to, let's say if it comes here like this and they start moving, both of them start moving with the same velocity v dash, let's say. So the momentum then will be m plus m into v dash, right? Minus I. This should remain conserved. This is your first equation, and the second is your conservation of energy, right? Half mv square, your kinetic energy initially, should be equal to some of it goes into potential energy mgh, right? Some of it is converted into potential energy, and when they both start moving with the same common velocity, you will also have a half m plus m into v dash square term, right? Now you have to solve both of them to get your v, so you can actually avoid all of this and go to the reduced mass frame to solve this particular problem. Let's see how. So whenever you have two masses like this, what you can go is you can go to a separate frame, and think of this both of them as a single mass, which is mm by m plus m. This is your mu. So this quantity mu has units of mass, as you can see, mass into mass by mass plus mass. That means dimensionally it's mass only, right? And this is what is known as your reduced mass. Now I can do this problem in one step without actually doing all that and solving all of that. I can use this particular equation: half into mu relative square, v relative square is equals to change in potential energy, right? Basically I'll apply conservation of energy, kinetic energy plus potential energy remains constant. I'll do the same thing here, but just that what I'll do here is my velocity from here, I've used the same thing here. My kinetic energy plus potential energy is equal to constant. This equation that you see here is the same thing as this, but here your mass is replaced. In this equation, my mass will be replaced by reduced mass and velocity will be replaced by v relative. That means what is the relative velocity between these two, right? Remember, only the relative velocity between these two is available for conversion in this frame, right? So there is an initial relative motion between them. This is having a zero velocity. Capital M's velocity is zero. Small m's velocity is v. So initial u relative is nothing but u, it's nothing but v, right? This is your u relative, initial relative velocity, because this is at rest and this is moving with v. But your v relative, which is your final relative velocity, that is zero. Why is that zero? Because both of them are moving with a common velocity v dash. So this will also be v dash this side, this will also be v dash, that will also be v dash, so v dash minus v dash will be zero. So v relative is zero. Now I'll simply use half into mu relative, where my mu is mm by m plus m into final velocity, final v relative, which will be 0 square minus half into mm by m plus m into initial u relative velocity, which is u relative 0 v square. That will be equal to work done by that will nothing be what I was trying to use was kinetic energy plus potential energy equal to constant. This I can equate it to minus mgh, work done by gravity, right? In fact if you rearrange, you'll get the same thing. That initial velocity was this, and initial potential energy was 0. Final kinetic energy in this frame is this. Final potential energy in this frame is mgh, right? So when you solve this, you get v in one step here. V is equals to just solve this particular thing. This m goes away. Yeah, you'll have a root 2 into m plus m gh, root 2 into m plus m gh divided by m, right? This will be your v, and then you can just put it in the momentum equation to get v dash. So if you see this thing was the same, just that your kinetic energy plus potential energy equal to remains constant is the same thing. Your kinetic energy expression changes. That is the only thing that changes. Your half into m is replaced by v, and u is replaced by u relative in this frame, right? So you'll have a v relative, you'll have a u relative, you'll have to use that and then balance the energy equation. You can get the answer in one step.